Okay, so we have kind of talked about we talked about 3 different types of motion, right? Well, no, sorry. 2 types of motion we talked about. One, so this is not one type of motion, but this is just what motion is, right? Motion is just when an object moves, right? That's just pretty self-explanatory, okay? And then we have 2 types of motion. So one is uniform motion. So this is where an object is moving at a constant rate in a straight line. Okay, so if you're like driving on the highway and you turn your cruise control on, and let's say you had like the best cruise control ever, so your speed or velocity would not fluctuate. Okay, if you're moving at a constant rate in a straight line, that is uniform motion. Okay, does anybody remember the other type of motion that we talked about yesterday? Yeah, perfect. Non-uniform motion. And this is when an object does not move at a constant rate in a straight line. Okay? When an object does not move at a constant rate. Cool. What do you think is more common, Mitch? Non-uniform motion or uniform motion?
I think uniform.
Really?
Non.
When you walk, do you always walk at the same pace?
No.
No, right? Depends like maybe who you're walking with, or if you're in a rush to get somewhere, right? Yeah, so non-uniform motion is going to be the most common type of motion, okay? Objects are changing their motion all the time, right? Even when you have a planet in orbit, so like for our Earth, which is rotating the sun, right? That does not even have a uniform motion, right? As it is further away from the sun, it orbits at a slower speed, and as it gets closer to the sun, its orbital velocity increases, because we have the closer you are to an object, the more force of gravity you're going to experience, right? Cool. So yeah, non-uniform motion is more common. Okay. So we can graph uniform motion. We can also graph non-uniform motion. Okay. Tomorrow, when we do our lab graphing activity, we will very likely have non-uniform motion, but we will figure that out when we make our own graphs. Okay. So create a table of values for the following graph and calculate the average speed. Okay. So a table of values is what you're going to be doing. You're just going to compare the x values. So remember, this is the x-axis going horizontally. And we're going to compare those to the values of our y-axis. Okay? So we can just go ahead and make a little chart here. Okay, and we have some data points on here which are nicely laid out for us. Okay, so when we are at a time of 0, so we always have to start at the beginning of our graph, right? When we're at a time of 0, what is our displacement? Also 0, good. Now that I'm going, I realize I need to be more specific with my table of values. Okay? What is on the x-axis? Time. Okay? Good. So I'm actually just going to get rid of these, and I'm going to be better. So time is on the x-axis for sure. And let's assume these are in seconds. So let's include units on our table. Okay? And what is on our y-axis? Displacement. Good. And what are the units for that? Perfect. Okay. meters. And because displacement, is it a scalar or a vector quantity? Displacement is a vector quantity for sure. So let's say this is going north. Okay, so meters in the north direction. Okay, all right, now that we've cleaned that up. So our time is 0 and 0. For time 1, our displacement is at 10 meters. For time 2, our displacement is at 20 meters. Time 3, our displacement is 30, and 4, and 40. Okay, so here is our table of values, and now we need to calculate the average speed during the 4 seconds. Okay, so from yesterday, we said, and this should say velocity, because this is a vector quantity. Okay, so yesterday we said average velocity is equal to total displacement over total time. Right, so our displacement is 40 meters north. Divided by our time interval, which is 4 seconds. So our average velocity is equal to 10 meters per second north. Okay? Good. So what if I wanted, so what we've just done, so we calculated the average velocity during those 4 seconds. And what we have essentially just done, we have just calculated the slope of this graph right here, from this point to this point right here. Does anybody remember from your math classes maybe how to calculate slope on a graph? Yeah, Maria?
It's rise over run.
Perfect. Okay, so slope is equal to rise over run. So rise is going to be on the y-axis, right? And run is going to be on the x-axis. Okay, so how fast is it moving upwards with respect to our horizontal movement on the graph, right? So slope is equal to rise over the run. Now in a displacement time graph, okay, so it's important that we watch our axes and what the units are, or like what our graph even is, okay? So for a displacement time graph, what is the rise? What's on the y-axis? Displacement, yep. So slope is equal to, and I'm just going to say displacement because I don't have enough room, is equal to displacement. And what is on the run? What's on the x-axis? Time, right? So slope over change, so slope is equal to displacement over time, which makes sense because from yesterday we know that our average velocity is equal to displacement over total time. Okay? So what we've just done, so when we find the slope, okay, and this is really important, so make sure you write this down. When we find the slope, on a distance or a displacement time graph, okay? On a distance distance slash displacement dash time graph, we are calculating the average velocity. Okay, that is very important. Make sure you guys know that. And it all stems back and ties back into slope is equal to the rise over the run. Okay? So let's get to the graphing portion and the notes that I handed out on Monday. Do you have them, Ryan?
No, I wasn't grabbing it.
Okay. Give me 1 sec, and I'll find them for you, okay? Any questions about this so far? Doing alright? Okay, cool. Okay, so now you guys can take this table of values and we're going to make a graph from it, okay? So time is going to go on the x-axis and displacement is going to go on the y-axis. So start plotting these points. Okay. And just before you guys get going and do something that I'm not going to like, I just want to, so we'll start off with our graph, okay? Time is going to go on the x-axis, so make sure you include your units, okay? And then displacement, let's say this is meters north, and displacement will go on the y-axis, okay? Time almost always goes on the x-axis, okay? Because time is a controlled variable, okay? And we always want to put the responding variable on the y-axis, okay? So my time range is 0 to 4. When you guys are making graphs, you never want your last data point to be like at the end of the graph. Okay, you always want to have a little bit of extra space there, okay? So this can be 5, 4, 3, 2, 1. And it doesn't have to be perfect because this is just a sketch, okay? It's just a sketch, but we still need to have consistent scaling on our axes, right? You can't do like 1, 6, 7, 9, 10, right? You would have to go up by a consistent amount each time. So it'd have to go 1, 2, 3, 4, 5, or 2, 4, 6, 8, 10, or like 3, 6, 9, 12, 15, right? It can't be all over the place. It has to have a consistent scaling, okay? And same with our displacement. They need to have a consistent scaling. So my range of displacement is 0 to 25. So what would be a good like maximum value for my displacement on the y-axis? Do I want to end right at 20, Mitch? No, so like 25 maybe would be all right. Yeah, 25 would be okay. And then we'll have 20, 15, 10, and 5. This can be 0. And what have I not labeled yet on this graph, other than my data? What does a graph always need? A title, yeah, you bet. So this will be displacement versus time. And that's totally fine with me, okay? Just displacement versus time. But you need to have a title for it, okay? So yeah, so we can just go ahead, now that we have our axes labeled and a title, we can just go ahead and plot this data. Okay, so our first point is at 0 and 0, so that's right here. Our second point is at 1 and 5, 2 and 10, 3 and 15, 4 and 20, and 5 and 25. The displacement is going up by a consistent amount each time. So Tanner, is this uniform motion or non-uniform motion?
Uniform.
Yeah, perfect. Okay, good. Because the displacement is going up at a consistent rate per time interval. Okay, after you've plotted your points, some math teachers might say don't make a line of best fit. Some people will say make a line of best fit. I think it helps us to make a line of best fit, so let's go ahead and draw one. Now, if you were drawing one that's not a sketch, you'd use a ruler, of course, and you're going to try to make it so there are an equal amount of points above your line of best fit and below your best fit. Okay? In this case, because it is a linear graph, it's just a straight line, right? It's going to be impossible to have a straight line and have like 2 points above it and 2 points below it, right? But if it was non-uniform motion, that's when our line of best fit would be kind of helpful for us, okay? But anyways, so I'm just gonna go ahead, and that's kind of our line of best fit. Now, if I calculated the slope of this displacement time graph, what would I be finding? What would I be calculating? The rise over the run, yeah. But what does that tell me?
Average velocity.
The average velocity, okay? Good. The average velocity. And our units are going to help us for that too, okay? So, if you wanted to calculate the slope of this, so you'll see m probably as slope, right, from your math class. Okay, so m, or maybe I'll just say slope, because I don't really care about m. So slope is equal to rise over the run, which I could expand that to the rise. What is my rate of change in the y-axis? So it is equal to delta y, and my change in my run is going to be my change in x, right? What is on the y-axis here? Displacement, yeah, good. So my change in y is going to be my change in displacement. And what is on my x-axis here, Ariane? Time, yep, for sure. So it's going to be delta t. Now, anytime that I see a delta, what does that mean, Joanna?
Change.
A change in something, and it's going to be like the final minus the initial, right? So this is going to be displacement final minus displacement initial, and same with the time final minus time initial. Now, I want to calculate slope for this whole graph. Okay, so what is my D2 and my T2, or my final time and my initial time? Sorry, my final displacement and my final time going to be? Right up here, right? This is the end of our data. So at this point, we have 4 is our time, and our displacement is 20. Okay? And if I want to do the slope for the whole line segment, I'm going to measure the rate of change from right here, okay, which is 0 and 0. So my final displacement is 20 meters north. And my initial displacement was 0, right? Minus 0 meters north. Divided by my final time, which is 4 seconds, right? Minus my initial time, which is 0 seconds. Okay, so 20 minus 0 is just 20, and 4 minus 0 is equal to 4. So slope is equal to 20 meters north divided by 4 seconds, which is going to equal 5 meters per second. Okay, units are our friend. They're going to help us communicate that the slope is average velocity, right? So average slope is going to be 5 meters per second, right? Meters per second north. Okay, and when you guys are like doing this calculations, you don't need to say slope is equal to rise over the run, which is equal to delta y over delta x, which is equal to delta d over delta t, which is equal to all that, okay? I just wrote it that way today because I wanted you guys to see like the relationship of how slope is calculated and how that's going to reflect our average velocity for that whole, for this motion. Okay? How do we feel about graphing? Just in general, like, okay? Do we hate it? It's okay? No complaints? Alright, neat. Okay, is everybody okay if I change the slide? We're cruising? Alright. Okay, so now I want you guys to create a velocity time graph using the following data. Okay, so we're still, what's going to go on our x-axis here? Time, yeah, good. And what is going to go on our y-axis? Velocity, perfect. And let's say this is going south, just for fun. Okay, so velocity, and then don't forget our units, meters per second south. Okay, so from there, I would like you guys to do the rest on your own, please. And then, so if I wanted to ask you guys to find the slope of this line, so slope is rise over run. In this case, my velocity is on the y-axis and my time is on the x-axis. Okay, and this is VF minus VI over TF minus TI. Okay, so my last coordinate up here is again 4 and 20. And my first coordinate here is 0 and 0. So my slope here is going, so my final velocity is 20 meters per second. 20 meters per second minus 0 meters per second, which is my initial velocity. And then over the change in time, which is 4 seconds minus 0 seconds. So a slope is equal to 20 divided by 4, which is 5. And my units on that is meters per second squared, right? Meters per second divided by seconds, okay? Meters per second squared. Good. I have another trick for you guys. So, I'm just, okay, so make sure you guys get this slope down. I just need to get rid of it because I'm going to work actually under this line right now. Okay, so we got our average acceleration for this time period, right? That's what we just calculated. This slope is the average acceleration for this time period. Okay? Good. Okay, so one other thing that you guys can do with the velocity time graph, okay? If you find the total area underneath the curve, so the area underneath this curve, it will tell us the total displacement of the object in this time. Okay, so let's write that down as well. If we find the area under the curve on a velocity time graph, so v dash t, we find the total displacement. Okay, so that's a big one. Let's write that down. Okay, you need to know that. You need to know how to find displacement given a graph question. Okay. So in this case, in this question, we just have one triangle, right? So it makes it kind of easy for us to find that. In some cases, your graphs might look something like this. Okay, and in that case, you could just find the area of 1, 2, and 3, and then add them all up together. Okay, so that is going to be something we need to know how to do. Okay, so can anybody remind me how to calculate area of a triangle? Perfect. Perfect. So the area for a triangle is equal to base times height divided by 2. Perfect. Okay, so what is my base? Is right here. So it is 4 seconds. Okay, units are important here as well because they're gonna help us. Okay, so area is equal to 4 seconds times the height, which is 20 at its highest point, right? So 20 meters per second divided by 2. So a second multiplied by a meter per second, our seconds are going to cancel. And what units are we going to be left with?
Meters.
Meters, which is perfect because that is the units for displacement. Yay. Hopefully that was like full circle right there. Hopefully there was a few connections being made. So 4 times 20 is 80 divided by 2 is 40 meters. So this is my displacement is equal to 40 meters south. Okay, so we learned a few things today. So if we bounce back to our displacement time graph, what can we find if we calculate the slope of a displacement time graph?
Average velocity.
Average velocity. Good. If we have a velocity time graph and we calculate the slope of a velocity time graph, what do we find? No, that's area underneath the curve. If I'm,
Acceleration.
yeah, perfect, is my average acceleration. So if I calculate the slope of a velocity time graph, I am finding my average acceleration for that time period. Okay, and then Abe, if I am calculating the area underneath a velocity time graph, what am I finding? The total displacement, yeah, you bet. Okay. Questions about that? Feeling all right? Okay. Let me see. I think I have a graphing example for us. And if it's not in here, it's on your assignment. Yeah, it is on your assignment, but that's okay. Let's just make one up right now. Okay, so let's say a runner starts from rest. So if he starts from rest, initial velocity, 0, good. A runner starts from rest and starts running. He reaches a speed of 7 meters per second in 10 seconds. He maintains this speed for 20 seconds and then returns to rest in 5 seconds. So graph the runner's motion and find average velocity. Sorry? What am I finding on a velocity time graph if I find the slope? Find average acceleration and find total distance ran. Okay, so let's start with an axis. There it is. Okay, so this is a speed versus time. Okay, when you have a speed versus time graph instead of a velocity time graph, it's like the exact same thing, just we're not given a direction of where the runner's going. Okay? So this is on our quiz, by the way, that we have on Friday. Graphing quiz on Friday. Okay, so make sure you guys know how to do this stuff, okay? This one is definitely going to be on there. And not this exact question, but something like this. Okay, so on our y-axis, we will do our speed because time always goes on the x-axis. Okay, so speed is measured in meters per second. Okay, and you guys will also be graded on how you make a graph. Okay, and it's just a sketch. Okay, so it doesn't have to be perfect, but you still have to label your axes and have proper scaling. Okay, so speed is on the y, time is on the x, and when you are doing just like a sketch like this on a quiz, I am also okay if we just do our like points of interest. Okay. So we start from rest, so 0 and 0, so let's include 0 on our axis. And it reaches a speed of 7 meters per second, so let's say this is 7. In 10 seconds, okay, so our other time is 10. So here's our first point right here. So 7 and 10. He maintains this speed for 20 seconds. So 20, 30. So he stays at that speed for 20 seconds, right? stays at this speed for 20 seconds. So from 10 to 30, he's running at 7 meters per second, and then returns to rest in 5 seconds. So that's 40. It's going to be right here. Okay? So now let's connect our points. Okay. Now we have to divide this graph up into its shapes. So this is 10 over here. Sorry, it's not to scale. That's supposed to be a triangle. And again, it doesn't need to be perfect. Okay, so we've broken this up into 1, 2, 3 shapes. And instead of average acceleration for the whole thing, let's just do average acceleration between 0 and 10 seconds. Okay, so between 0 and 10 seconds. So part A and part B. So A, to find the average acceleration between 0 and 10 seconds. So to do that, we would just be calculating the slope between there, right? So slope, or average acceleration average is equal to rise over the run. And this is only true on a speed or a velocity time graph, okay? So acceleration average is equal to rise over the run. In this case, our rise is 7 meters per second minus 0 meters per second over 10 seconds minus 0 seconds. So for that, I don't know, I need a calculator for that, is 0.7 meters per second squared. Okay, and then for part B, we're just going to calculate the areas of these 3 shapes and then add them together. Okay? So for shape 1 is a triangle, so it is length times, or whatever, length times width divided by 2. So my length is 10 seconds. My width, well, base times height, whatever you want to call it, okay, is 10 seconds times 7 meters per second divided by 2, because it is a triangle. So 10 times 7 is 70, divided by 2 is 35. Seconds are going to cancel there. And so 35 meters is my displacement during the first 10 seconds. Okay, so for part 2, we have a rectangle, which is nice. Area for a rectangle. Base times height, good. Or length times width, whatever. I'm just gonna be consistent here. So length times width. So my length is from 10 to 30, so it's 20 seconds. And times my height, or my length, which is 7 meters per second. So 20 times 7 is 140 meters. Again, my seconds are going to cancel. Now for area 3, so my length is 5 seconds times my height of 7 meters per second divided by 2. So 5 times 7 is 35, divided by 2 is 17.5. Last step, just add up these 3 numbers and you will have arrived at your total distance covered, which is 192.5 meters. Questions? Concerns? Comments? Are we good back there?
Yeah.
Go, Washington.
When Harry gets back. Okay, so make sure you guys are able to do this on Friday's quiz. Okay, that is, it's gonna be on there.